Okay, here we are with part 3 of the energy notes. We're going to start with efficiency. In any machine, some energy is transformed into atomic or molecular kinetic energy, making the machine warmer. The previous examples of machines, we really haven't talked about machines, but I'm going to kind of show you some stuff in class about machines, are considered to be ideal because the work input was transferred to work output. So whatever work you put in the machine would come out of the machine, so they were equal. In a real machine, when a simple lever rocks about its fulcrum or a pulley turns about its axis, a small fraction of input energy is converted into thermal energy. So you lose energy as heat. You're not very efficient, is what it's saying. The efficiency of a machine is the ratio of useful energy output to total energy input, the percentage of the work input that is converted to output work. So basically, if you look at our formula here, efficiency is your output divided by your input. And you're really, in the real world, you're not going to get 100% because you're going to lose some of that energy to heat. So if we put 100 joules of work on a lever and get 98 joules of work out, the lever is said to be 98% efficient because you lose 2 joules of work to heat. Or a pulley system, a large fraction of energy input is lost as heat. For example, if we do 100 joules of work, the friction on the pulley as they turn and rub against the axle dissipates 40 joules of heat, so you're only 60% efficient. Inclined planes. An inclined plane is a machine also. Sliding a load up an inclined plane requires less force than lift it vertically. This is something to remember if you ever try to move something. Picking it up and moving it is harder than just sliding it up an incline. Pushing the block of ice 5 times farther up the incline than the vertical distance it's lifted requires a force only 1/5 its weight. If friction is negligible, we need to apply only 1/5 the force. The inclined plane shows this has a theoretical mechanical advantage of 5. You see he's only lifting this 1 meter over here, but he's pushing this up 5 meters. It requires the same amount of force, or you need much less force to move this up because you can move this 5 meters as opposed to 1 meter with the same amount of force. Okay, an icy plank used to slide a block of ice up to some height might have an efficiency of almost 100%. When the load is a wooden crate sliding on a wooden plank, both the actual mechanical advantages and the efficiency will be considerably less. Friction will require you to exert more force, a greater work input, without any increase in the work output. So sliding ice is pretty easy to do, but if you slide, it's saying like wood on wood, you're going to get more friction, so you're not going to be as efficient because of the grinding between the two surfaces. Efficiency can also be expressed as a ratio of actual mechanical advantage to theoretical. So another way to look at efficiency is the actual mechanical advantage, what do you got, divided by the theoretical. And this is usually going to be less than 1. Now you have complex machines. This auto jack shown in the inclined plane wrapped around the cylinder. As it goes around, you turn around and it basically jacks up the car. It moves at a very small distance here, 2 millimeters, and you have something that turns in a circle around and around to jack up the car. So if we look at that, the circular distance the handle is moved is 500 times greater than the distance between the ridges, because you saw how far it went around the circle was much greater than the distance it went up. Then the theoretical mechanical advantage of the jack is 500. There's a great deal of friction in the jack, so the efficiency might be about 20%. This means that the jack actually multiplies force by about 100 times. So the actual mechanical advantage is only 100. The automobile engine is a machine that transforms chemical energy stored in fuel to mechanical energy. The molecules of the gasoline break up as the fuel burns. So you burn the fuel in your gas tank. Then the carbon atoms from the gasoline combine with oxygen atoms to form carbon dioxide. The hydrogen atoms combine with oxygen and is released. Converted energy is used to run the engine, not the energy, the engine. So basically, you're not going to get the most efficiency out of your engine because you are releasing some stuff as discard. Transforming 100% of thermal energy into mechanical energy is not possible. Some heat must flow from the engine. Friction adds more to the energy loss. Even the best designed gasoline-powered automobile engines are unlikely to be more than 35% efficient. Think about that. The cars you drive are only 35% efficient, meaning that 65% of what you're needing for energy is lost. Okay, a child on a sled that weighs 500 newtons is pulled up a 10-meter slope that elevates her a vertical distance of 1 meter. What is the theoretical mechanical advantage of the slope? The ideal or theoretical mechanical advantage is the input divided by output. So you put in 10 meters, and she was going to go a distance of 1 meter, so 10 is your ideal or theoretical. Why can't a machine be 100% efficient? Remember we said because you get a lot of heat loss or friction loss. You get energy that is lost in either heat or the friction form. Okay, energy for life. This is more energy stored in the molecules in food than there is in the reaction product after the food is metabolized. This energy difference sustains life. Every living cell in every organism is basically like a machine. Like any machine, living cells need an energy supply. In metabolism, carbon combines with oxygen to form carbon dioxide during metabolism. The reaction rate is much slower than combustion, and the energy released is what the body is released as it is needed by the body. So you burn up your reserves to create energy in your body. Only green plants and certain one-celled organisms can make carbon dioxide combined with water to produce hydrocarbon compounds such as sugar. This process called photosynthesis, we don't do that as humans, requires an energy input which normally comes from sunlight. Green plants are able to use the energy of sunlight to make food that gives us and all other organisms energy. What role does energy play in sustaining life? We just talked about that, how we basically get energy from the food we eat. Sources of energy. The sun is the source of practically all our energy on Earth. As the sun comes down, we get most of our energy produced by it. All right, solar power. Sunlight is directly transformed into electricity by photovoltaic cells. We use these energies in sunlight to generate electricity indirectly as well. Sunlight evaporates water, which later falls as rain. Rainwater flows into rivers and into generator turbines as it returns to the sea. Solar shingles look like traditional asphalt shingles, but they are hooked into a home's electrical system. You can put these on the side of your house and have your house basically work as a battery. Wind caused by unequal warming of Earth's surface is another form of solar power. The energy of a wind can be used to turn generator turbines within specifically equipped windmills. Harnessing the wind is very practical, and the energy it produced is stored for future use, such as in the form of hydrogen. Fuel cells. Hydrogen is the least polluting of all fuels because it takes energy to make hydrogen. To extract it from water and carbon compounds is not a source of energy. It's very hard to get to use hydrogen as a fuel source. An electric current can break water down into hydrogen and oxygen, a process called electrolysis. Basically, you break these down to use its parts. If you make the electrolysis process run backwards, you have a fuel cell. In a fuel cell, hydrogen and oxygen gas are compressed at electrodes to produce water and electric current. And this electric current is what you can use then to run things. Nuclear and geothermal energy. The most concentrated form of usable energy is stored in uranium and plutonium, which are nuclear fuels. Earth's interior is kept hot by producing a form of nuclear power, radioactivity, which has been with us since the Earth was formed. A byproduct of radioactivity in Earth's interior is geothermal energy. Geothermal energy is held in underground reservoirs of hot water. In these places, heated water near Earth's surface is tapped to provide steam or running turbo generators. What is the source of practically all of our energy on Earth? I don't know. What is the source of practically all the energy on Earth?